All right, so we're still in section 5.2, and we're ready to finally develop a complete test for diagonalizability of matrices and transformation, building on all those results that we proved last time. So just to remind you, we looked at a couple of things. One of them was this idea that whenever a linear operator is diagonalizable, then its characteristic polynomial must split. We've seen that implication, but then we've also seen that it is not an if and only if condition, so there are counterexamples. However, it has to be part of the requirements for a transformation to be diagonalizable, because it is implied by that. So provided that the characteristic polynomial splits, you make a list, a complete list of the distinct eigenvalues of T. There are k of them listed here. That doesn't mean that V has dimension k, of course. So T is defined on a finite dimensional vector space V. Let's say it has dimension n. But only k eigenvalues are distinct because they can come with multiplicities, right, higher than 1, right? So let's say an eigenvalue has multiplicity 2, another one has 1, another one has 5. I'm just choosing one of each, right? So k will be less than or equal than n. Okay, so it turns out that under these conditions, T is diagonalizable if and only if the multiplicity of every lambda is the dimension of its eigenspace. Okay. And more than that, in case it is diagonalizable, here is how you find that basis of eigenvectors. You just take a basis for every eigenspace, and then you take the union of those bases, and that will be your basis of eigenvectors. Let's look into the proof of this. I'm going to say part A, however, B will be somehow embedded in A. You're going to see that soon. So part A is an if and only if kind of proof, so let's go in both directions. So let's just assume first that T is diagonalizable. By definition, that means that there exists a basis beta, let's say, for V consisting of eigenvectors for T. Okay, so there are n elements in beta. We assume that the dimension of V is n. But how do we find eigenvectors for an operator? Well, we find them in each eigenspace, right? We take them from the eigenspaces. So let me just denote by beta I the intersection between beta and the eigenspace corresponding to the eigenvalue lambda I. And we're going to do this for every I between 1 and k. Right? So beta is going to have n eigenvectors in there. Some of them will come from the eigenspace of the first eigenvalue. Some will come from the eigenspace of the second one, and so on. So beta I denotes the ones that come from E lambda I. And let's denote by ni the number of eigenvectors in E lambda I. So the cardinality of beta I. Okay. So if you look at the statement, what we need to prove is that the multiplicity of lambda I, let me give this a name. Let's call that mi. The multiplicity of lambda I is equal to the dimension of the I corresponding eigenspace. Let me call that bi. Okay, so the eigenspace of lambda I has a dimension which we'll call d sub I. Now, we said that beta I has n sub I vectors in there, right? And they are part of a basis, so they are independent, those n sub I vectors in E lambda I. That means that n sub I cannot exceed the dimension of E lambda I, correct? Because if you have an independent set, you can expand that to a basis. So n sub I is less than or equal and the dimension of E lambda I, which is something that we called D sub I. Okay. And more than that, according to a theorem from last time, the dimension of an eigenspace will never exceed the multiplicity, the algebraic multiplicity of that eigenvalue, and that's something that we call M sub I. And that holds for every I between 1 and k. All right, but I'm going to look at some sums now. I want to sum all those numbers, n1, n2, up to nk. What do I get? Well, let's see how we created those ni. So those were the cardinalities of beta i's, and those were pieces of that basis beta, right? So the overlap between beta and every eigenspace. Now, if you remember from last time, if you pick vectors from two distinct eigenspaces, there will never be an overlap other than the zero vector, correct? So that means if I want to find the sum between n1 and so on up to nk is the same as adding the cardinalities of those beta i's, right? There is no overlap. So if I put all those together, I'm actually getting back the basis beta, right? It's like having a partition of beta in the end, right, into k sets. Okay, so this is the cardinality of beta, but what is the cardinality of beta? Beta was a basis for V, and V we said had n elements, right? And dimension n, sorry. So the cardinality of a basis is n. All right, so n1 plus nk is n. Thus we'll be using the numbers on the very left of this inequality here. And now I'm going to look at the far right. Remember that what I'm trying to prove is that mi equals di, right? The multiplicity equals the dimension of the eigenspace. So now I'm going to look at the sum of mi's. Now, mi's are the multiplicities, right, of each eigenvalue. Where are they coming from? From the characteristic polynomial, right? The characteristic polynomial splits into a product of first degree polynomials, each raised to some power, and that gives you the multiplicity, right, for each eigenvalue. What is the sum of those powers? It's n, correct. You have a polynomial of degree n that splits into, I don't know, t minus 1 to the third times t minus 2 to the fifth times t minus whatever. The sum of those powers, right, is going to just be the degree of the polynomial. Right, so it's still n. But if I look at the inequalities that I have here for every I and add them all up, on the far left, I get the sum of all ni's being less than or equal than the sum of all d sub i's less than or equal than the sum of all m sub i's. Again, that's by adding all those inequalities. And the sum of all ni's, we just noted, is n. And the sum of all mi is also n. So how can this happen unless that sum in the middle is also n? So the sum of di is n and is the same as the sum of mi. Yes?
Where did we get that the d sub I is less than equal to m squared from?
Which is this one here?
Yeah.
There was a theorem from last time which said that every eigenspace has a dimension that will never exceed the multiplicity of its eigenvalue, the eigenvalue that is defining it. Which theorem number that was? I'm not sure. 5-7? Right, so that's exactly what we proved. The dimension of an eigenspace is between 1 and the multiplicity of that eigenvalue. So that's exactly what's written there. Okay, so this is what we have now, that the sum of di equals the sum of mi. That's not really what we need. What we wanted to show is that the dimension of every eigenspace equals the multiplicity, right, of each eigenvalue. Which in general, right, doesn't hold. If the sum of a set of numbers equals the sum of another set of numbers, it doesn't mean that they are equal individually. However, here, because we have this inequality, it's going to work out nicely in the following sense. If you subtract the sum of di from the sum of mi, I'll get 0 for sure. But I can group them like this. Right, subtract the sum on the left from the sum on the right, you get 0. And it is a sum of k numbers, each of the k numbers being greater than or equal than 0, because di is less than or equal than mi. So how can the sum of k non-negative numbers be 0 unless each of them is 0? Okay, so what we proved is that in case that t is diagonalizable, so a basis of eigenvectors exists, then this must happen, that every eigenspace has a dimension equal to the multiplicity. Let's go backwards. Oh, and more than that, if you look at part B now, part B says, if t is diagonalizable, and beta I is a basis for E lambda I, then this is how I get the basis of eigenvectors. And that's actually part of our proof here, right? We said that beta I is the intersection between the basis of eigenvectors and the subspace lambda I. Beta I had n sub I vectors in there, which turned out to be equal to di and equal to mi, right, in the same way as here. So you're going to get a maximal linearly independent set in each E lambda, so it's a basis. So somehow B is embedded into this proof. Okay, now going backwards. Going backwards in part A means that every mi equals di, and you want to show that t is diagonalizable. Okay, so in order to show that an operator is diagonalizable, we have to come up with a basis of eigenvectors, right? This is all we need. And we already have an idea how to do that. We're going to take a basis for each E lambda I and just take the union of those things and hope that it is what we get. So let beta I be an ordered basis for E lambda I. We're going to do this for every I. And we're going to define beta to be the union of all those bases. Okay. We already know that this beta is linearly independent, and that was the last result we proved last time, was saying exactly this. If you take a bunch of independent vectors in an eigenspace, then take another set of independent vectors in another eigenspace, you put them together, it's still independent. That's the last theorem from last time. So this beta is linearly independent. In order to become a basis for V, it's enough to just show that it contains n vectors, right? An independent set of n vectors will be a basis. All right, but what is the cardinality of beta? Again, there is no overlap between those beta i's. We know that already. So the cardinality of beta is just the sum from 1 to k of the cardinalities of beta I. What is the cardinality of beta I? That's how big the basis for E lambda I is, and that is something that we called D sub I. By assumption, D sub I, though, is M sub I. And we get back now to the sum of the multiplicities, which again, from the characteristic polynomial, turns out to be n. And that's exactly what we need. So in conclusion, beta is a basis consisting of eigenvectors, and that makes T diagonalizable. And we're done. So in conclusion, what do we need to do when we're given a linear transformation or a matrix and we're asked to show or to determine whether it is diagonalizable? There are two things that we need to look at. One of them is this. The characteristic polynomial must split. That is the assumption of this theorem, right? So you have to check the characteristic polynomial. If it doesn't split, you're done. It's not going to be diagonalizable. If it splits, you move on, right? You move on where? You make a list of all the distinct eigenvalues. For each of them, you find the eigenspace, right? You find the dimension of each eigenspace. If for every eigenspace, the dimension equals the multiplicity of that eigenvalue, where it came from, you're done. It's diagonalizable. If you find one where this fails, you're done again. It's not going to be diagonalizable. Make sense? Do you want to see an example? Yeah? This is 3a in section 5.2. For each of the following operators T on a vector space V, test T for diagonalizability. And if T is diagonalizable, find the basis beta consisting of eigenvectors. T on P sub 3 of R, so operator from P sub 3. I don't know if I want to do this because P sub 3 has dimension 4, so that would give us a 4 by 4 matrix to compute the determinant. So let me take that back. And let me go to part D, which is only defined on P2. So 3 by 3 is answer to work with. So an operator on P sub 2 of R, T of f of x is f of 0 plus f of 1 times x plus x squared is T diagonalizable? If yes, find that beta, which is the basis of eigenvectors for P sub 3 of R. Okay, so what do we need to do? We need a characteristic polynomial, first of all, to see if it splits. How do we find the characteristic polynomial? We need the determinant of T in some basis of your choice. Let me call it alpha because I already used beta. Minus T identity, right? You have to choose a basis. A basis for what? For P sub 2 of R. So why not choose the standard basis, right? We don't have to go further than that. So let alpha be 1x x squared. Okay. All right, let's figure out the matrix of T in this basis. So T of 1, what will it be? F of x equals 1, constant equal to 1. So f of 0 is 1, right? F of 1 is 1. So the first column is 1, 1, 1. T of x now f of 0 is 0, f of 1 is 1, right? So you're just left with x plus x squared, so 0, 1, 1. And T of x squared. Same thing, right? All right, so the characteristic polynomial was the determinant of the matrix 1 minus T, 0, 0, 1, 1 minus T, 1, 1, 1, 1 minus T. Let's see what this is. 1 minus T cubed plus 0 minus 0 minus 1 minus T. And that's it. So let's factor it. So you have 1 minus T minus 1, 1 minus T plus 1, right? And at this point, I realize that is not a very nice example, or very, it doesn't say much, but anyways, let's continue. Why am I saying that? Because this operator has 3 distinct eigenvalues, in which case we already know it is diagonalizable, right? We've seen that before. If an operator has n on a space of dimension n has n distinct eigenvalues, it's going to be diagonalizable. Each of multiplicity 1. All right, so 3 distinct eigenvalues means it's diagonalizable. If you don't want to refer to that theorem from last time, we can also look at it in the following way. Without computing anything, I know that the eigenspace of lambda 1 will have which dimension? It's a dimension that sits between 1 and the multiplicity, which is also 1, right? So it's 1. E lambda 2 will have dimension 1 as well. And E lambda 3 will also have dimension 1. So you're going to choose one vector from each, right? Let's continue. Actually, the question is asking you to, if yes, find beta, right? So who is beta, the basis of eigenvectors? Or how do we find it at least? Well, I need one vector from E lambda 1, non-zero, a vector from E lambda 2, and a vector from E lambda 3. And just to actually go ahead and compute them, right, and find a basis, if you want, for each. So let's take the first one, E lambda 1. How do we find the basis for that? Well, E lambda 1 is defined to be the null space of T minus lambda 1 identity. Okay, what matrix is associated to this? Lambda 1 is 2, so you just subtract 2 from this matrix here, right, the matrix of T. So that means negative 1, 0, 0, 1, negative 1, 1, 1, 1, negative 1. To find a null space, I need to find those vectors, x1, x2, x3, that give you 0 here. Which means this system of linear equations and something is not right. Why not? Because it's 1 minus t squared minus 1 squared is like a squared minus b squared is a minus b times a plus b. Oh, I see what I did. Sorry. I replaced x2 by 0 in the second and third equation, while x1 was the one that was 0. See what I did here? x1 was the 0 one. So that means negative x2 plus x3 is 0. And x2 minus x3 is 0, which is 1 in the same equation. Okay, that was the problem. Okay, so basically we get x1 is 0 and x2 equals x3. Let's say x3 is the free one. So E lambda 1 is the set of vectors that look like this: 0, x3, x3. So all you have to do now is to choose a non-zero vector from this set to put it in your basis beta. Now, of course, I'm going to choose 0, 1, 1, but you can choose 0, 3, 3 if you would prefer to do that. Why would you choose 0, 3, 3? Let's say that through the computations, you get 0, 1/3, 1/3, and you don't want to work with that. You can choose 0, 1, 1 instead, right? You can choose any multiple, non-zero multiple of that vector. Okay, so this thing will go into beta. Will be the first vector of beta. Okay, so you're done with E lambda 1, then continue with E lambda 2. And do the same thing. So do you want to keep on doing this, or it's pretty clear? You want to finish this till the end? Yeah? Okay, E lambda 2. E lambda 2 was associated to this one here, to the eigenvalue lambda 2 equals 1. So you have to do the null space of P minus identity, if lambda 2 is 1. So I'm just subtracting 1 from the main diagonal of this matrix, so I end up with 0, 0, 0, 1, 0, 1, 1, 1, 0. And I need to find all those vectors, x1, x2, x3, that satisfy this property. So another system to solve. First equation is just 0. x1 plus x3 is 0. And x1 plus x2 is 0. So basically, x2 is negative x1, x3 is negative x1, and x1 is 3. Okay, like this. So E lambda 2 is the set of vectors that look like this. So it is the span of this vector. 1, negative 1, negative 1, and this will go again into beta as your second vector. Okay, keep going, one more to go. E lambda 3, that corresponding to the eigenvalue lambda 3 equals 0. So that's the null space of T minus lambda 3 identity. So the null space of just T, right? So I'm just taking that original matrix. 1, 0, 0, 1, 1, 1, 1, 1, 1, right? And solving this system. So x1 is 0, and x1 plus x2 plus x3 is 0. Second and third equation are one and the same. So x1 is 0, x2 is negative x3, and x3 is 3. So E lambda 3 looks like this. Vectors of the form 0, negative x3, x3. So the span of the set containing the vector 0, negative 1, 1, and this vector goes into beta again. So what is beta? 0, 1, 1. 1, negative 1, negative 1. 0, negative 1, 1. This will be a basis for P sub 2 of R. Now, of course, if you want to make it look like it's in P sub 2 of R, you have to actually express them back into polynomials. So this first vector is in fact x plus x squared, right? The second is 1 minus x squared, and the third is negative x plus x squared. Okay. But what else can happen? So I said I didn't pick a really good example, but if you just choose one, there is no way to know what will happen, if it's randomly chosen. So in general, first of all, this characteristic polynomial must split, so you should be able to completely factor it in order to move forward, right? So let's say it does split, so it factors. But most of the times, you will not get three distinct terms like here. You will get, maybe less terms, but raised to some powers. That will give you multiplicities, right? And then for each eigenvalue, the multiplicity, so the power, should be the same as the number of vectors you get in the basis for that eigenspace, right? If you ever get anything that is not the same, you're done. It's not going to be diagonalizable. Okay? And I'm not going to try to choose another one, because who knows what happens. I think we've seen an example last time of something that was not diagonalizable. It was a matrix, a 3 by 3 matrix. In the end, it turned out that it had two eigenvalues, one of multiplicity 2, and each eigenspace had dimension 1. So it didn't work because of that. Okay. The example 2, if you want to look into that, it was this matrix here. So we've seen last time that it has two eigenvalues, 4 and 3. This one had multiplicity 1, this one had multiplicity 2. Okay, so the one of multiplicity 1 will have an eigenspace of dimension 1. You know for sure that you can choose one vector from there. So usually you start checking with the ones of multiplicities higher than 1, because that's where things might fail. So if you look at E lambda 2, which is the null space of A minus 3 identity, that gives you the matrix 0, 0, 1, 2, 1, 2, 0, 0, 0. So you end up with x1 equals 0, x2 is negative 2, x3, and x3 is 3. So this E lambda 2 consists of vectors looking like this. So it is the span of 0, negative 2, 1. So it has dimension 1. However, it corresponds to an eigenvalue that had multiplicity 2, so we should have been able to choose two vectors out of this space, and that is not possible. In conclusion, this matrix is not diagonalizable. Okay. Okay, so So now we're able to say if an operator or a matrix is diagonalizable or not. What do we do with that, right? So why does it matter? Well, if a matrix is diagonal, let's say, first of all, if a matrix is diagonal, that's a very nice property to have, right? Very easy to compute determinant, it's very, very simple to handle if a matrix is diagonal. Diagonalizable is kind of the next best thing. It's not diagonal, but it's going to be similar to a diagonal matrix. So how, from this process, do we get that a diagonalizable matrix is similar to a diagonal matrix? Well, here is the idea. If a matrix or an operator, but let's just look at the matrix, n by n. If an n by n matrix is diagonalizable, then there exists a diagonal matrix D still n by n, everything will be n by n here, and an invertible matrix Q such that A equals Q times D times Q inverse. And that's what we defined before to be similar, right? So remember, similar matrices have the same determinant. They have the same characteristic polynomial, same eigenvalues, right? So A and D are, very, very similar. So why does this hold? And who are those matrices D and Q? They are connected to the eigenvalues and the eigenvectors. D will turn out to be just the eigenvalues on the diagonal, right? Including multiplicities. There are n of them because the polynomial splits. So D is this. Those are the eigenvalues of A. Some of them could be the same, right? So if an eigenvalue has multiplicity 3, I'm just going to place it 3 times on the diagonal, right? In the end, I'm going to have n of them. All right, so who will this matrix Q be? Right. Here's how we get it. So A is diagonalizable, so there exists a basis for Fn consisting of eigenvectors for A. Fn, let's say it's Rn, because let's say we're using entries from R. Okay. And let beta prime be the standard ordered basis of Rn. What's that? E1, E2, En, right? 1, 0, 0, 0, 1, 0, and so on. Okay. We've seen before that the matrix of the left multiplication operator by A in the standard basis, which we call beta prime here, is A itself. Okay. What is the matrix of L sub A in the basis beta? Who was beta? the basis consisting of eigenvectors of A. It is that basis in which the operator, the matrix of the operator, is diagonal, right? That's how we started everything. The matrix of L multiplication by A is the same as, the diagonal that you get from A, because that's how you connect a matrix to a linear operator. So this is going to be D. Lambda 1 to lambda n. Okay. Now, there was a matrix a while ago that we called the change of coordinate matrix, to change from a basis to another basis. We call that Q. This will be exactly that Q. So Q is the change of coordinate matrix from beta to beta prime. So it changes from beta to beta prime. Okay. And the matrix of any operator, like L sub A, in beta prime, is Q times the matrix of that operator in beta times Q inverse. Right, that's something that we proved a while ago. We used this result before. Okay, LA beta is D. LA beta prime is A. Right? So we got that A is Q dQ inverse. I know that Q exists, but in applications it doesn't mean much. So let's look into it and see who exactly is this matrix Q. Q, if you remember, was the identity transformation on V, expressed from beta to beta prime. That's how it was defined, the change of coordinate matrix. Okay, beta was that basis consisting of eigenvectors, so let me call them V1 through Vn, and beta prime was the standard basis, E1 through En. So I'm going to find exactly who Q is in this setting next. It's a matrix, right? The first column of this matrix is given by the operator, which is the identity inside there, right? Applied to the first vector in beta, which is V1. Identity of V1 is V1, right? How do you express V1 in the standard basis? But V1 has n entries. V11, let's say, V12 up to V1n, because it's a vector, a 1 n by 1 or 1 by n vector, right? It has n entries. So to express that vector in the standard basis, you do the first entry times E1 plus the second entry times E2 plus the third entry times E3 and so on. So what's the first column then of Q? Then So it's the first entry of V1, let's call that V11, plus the second entry of V1. Plus the last entry of V1, right? Where V1 is just an n by 1 vector. Let's say those are the entries. So V1 expressed in the standard basis looks like this. So the first column is this. right? Who is that? Well, it's exactly V1, right? V1 placed vertically in the first column. What's the second column? V2, placed vertically like this again. And Vn. So what is this saying? Well, not only that A is similar to a diagonal matrix, but the matrix Q that makes the similarity possible is found just by placing those eigenvectors in the basis beta next to each other, right? So let me go back to one example, the only one example that we computed entirely, which was this one here, which you can't see if I make it that small. This is where we found beta, right? So for this one, the matrix Q is what? Use a different color maybe. What's the matrix Q? First vector is the first column. Second vector and third vector. Right? You just place them next to each other. What is the matrix D? That diagonal matrix? Well, it must have the eigenvalues on the diagonal. What were the eigenvalues? 0, 1, and 2, but doesn't matter in which order I place them. Because I can do a diagonal like 0, 1, 2, or I can do 1, 2, 0, or 1, 0, 2. Well, theoretically it doesn't matter, but once I made this choice here, that decides my choice for D. Because I decided to go with this vector first. Where was that vector coming from? Well, I don't know where, but it came from lambda 1. I think we placed them in decreasing order, right? So it came from 2. So then I'm going to place 2 first on the diagonal. The second vector came from the next eigenvalue, which I think was 1. And then the third one came from 0. So again, the order is not important, but once you make a choice in one of those two matrices, that choice will decide the order of the columns in the other matrix. So basically, with this choice of Q and that choice of D, what will happen for this matrix? 1, 0, 0, 1, 1, 1, 1, 1, 1. It's going to be Q, D, Q inverse. It's going to be the same as this. I'm not going to check it, but it should work. Well, you don't actually need to do this. Now, the reason you might need this is in general in applications, and I'm going to show you next, because you already know this matrix, right? If you compute Q inverse, you would only check that this relation holds, and it should hold if you did everything right, so I'm not worried about this. And now let's see how this is useful. I said it's going to be useful in general in applications, especially in computational kind of applications. So for example, let A be the following matrix. 2 by 2 over R. Find A to the power 2000, or any other number you choose. Which again, in computational matrix analysis might be something that you'll need. Now, of course, you can raise that matrix to the power 2000, but not with a calculator, right? Not by hand. So here's how you can do this by hand. It turns out that this matrix is not really arbitrary. It's going to be diagonalizable. So you compute its characteristic polynomial. Which factors into t minus 5 times t plus 1. So it has two distinct eigenvalues, right? Which automatically makes it diagonalizable. All right, so then A equals Q times D times Q inverse, right? Where Q is that matrix obtained by putting the eigenvectors next to each other. So we need to find the eigenvectors for each. I'm going to look into E lambda 1, a null space of A minus 5 identity. -4, 4, 2, -2. x1, x2 equals 0, 0. So basically x1 equals x2. And x2 is 3. So E lambda 1 is the set of vectors looking like this. So here's my first eigenvector. It is 1, 1. That will be the first column of the matrix Q, right? Because we put this eigenvalue 5 as first on the diagonal. Okay, let's look at E lambda 2. A minus -1 identity, so A plus identity. It's A 1, 4, 2, 3, so 2, 4, 2, 4. So you get x1 plus 2x2 equals 0. So E lambda 2 is the set of vectors that looks like this, negative x2, x2, x2 in R. So the span of -2, 1. Here's the second vector. So then, here is the matrix Q. 1, 1, -2, 1. Okay. So back to our question. A is Q, D, Q inverse, where D is 5, 0, 0, -1. And I want to find A raised to the power 2000, right? Okay. That is Q, D, Q inverse raised to the power 2000. So what happens when I raise something like this to the 2000? In this format, Q, D, Q inverse. Q, D, Q inverse, Q, D, Q inverse, Q, D, Q inverse. Something pretty nice happens, right? They just cancel 2 by 2, those two things. And this with the next one, they will just become the identity. So in the end, what is this? What do you get? Q times D to the 2000. times Q inverse. So you're reducing, computing the 2000th power of an arbitrary 2 by 2 matrix to computing the 2000th power of a diagonal matrix, right? But that's pretty easy, because a diagonal, when you multiply it to itself, what happens? You just multiply each entry on the diagonal. So d to the 2000, so let's see, q was 1, negative 2, 1, 1. d was what? 5, 0, 0, negative 1. So 5 to the 2000, 0, 0, negative 1 to the 2000. And then I need Q inverse. What is Q inverse? I think it's this one, right? For a 2 by 2 matrix, remember how to find the inverse is 1 over the determinant. Determinant is 3. Times, and then you switch the entries on the main diagonal and you put the negative sign on the off diagonal. So I switched 1 and 1, and then it doesn't do anything, and then 2 and negative 1. Just multiply the negative 1 the off diagonal. All right, so I'm not going to do this, but in the end, it's just the product of 3 2 by 2 matrices that you have to compute in order to find any power of that original matrix A. And that, again, A has to be diagonalizable in order for this to work. So that's another usefulness, let's say, of diagonal matrices. Questions? So we're done with diagonalizability. Start this. Invariant subspaces and the Cayley-Hamilton theorem. So I think you already came across this notion of an invariant subspace. There was something in one of the homeworks that was assigned related to this, but let's go back anyways to this idea. So you have a linear operator on a vector space V, and then you're taking the subspace W of V. So subspace W of V is called T invariant if this thing holds. If when you apply T to something in W, you still land in W. That's not something that is guaranteed, right? Because if you take an operator on a big space and you just take a smaller subspace in there, apply T to an element in the smaller subspace, you can easily get out of that subspace, right, in the image of T. But if you don't, so if you land in W again, you're going to say that W, your choice of W was T invariant. So let's look at some examples of such things. Simplest example. Yeah.
How does this become an isomorphism?
T would be an isomorphism from what? From V to V?
Yeah. Not to itself.
But an isomorphism means T is 1 to 1 and onto, right? I'm making no assumptions regarding this. T could be anything, isomorphism or not. It's just a linear transformation. The assumption in the definition is not about T, it's about the choice of subspace W. So for the same T and same V, a certain subspace that you choose could be T invariant, another one might not be T invariant, right? So it's a matter of the choice for W. So here's one choice. Very simple choice. W is containing the 0 vector only. T is an arbitrary linear transformation on this vector space V, in which I'm taking this W. What happens if I apply T to an element of W? Well, I only have one element, 0. If I apply T to 0, I get 0. So I'm still in W, right? So this set is the invariant. The other extreme subspace is the entire V. If I apply T to something in V, can I land outside V? No way. Everything happens inside V. So this V is also the invariant. Since T of x is in V for any x in V. All right, so those would be the extremes. So let's just look at something in between. Here's another subspace of V, the null space of P. Null space of P consisting of all those vectors that T maps where to 0. So what happens if I apply T to an element of its null space? It goes to 0, but that's still part of the null space, correct? So it's the invariant. Range. So everything in the image of T. If I apply T to a vector V in the range, what do I get? I don't care what I get, right? But it's in the range anyways, because it is a T of something. So it's in the range. Okay. Let's say that lambda is an eigenvalue of T. And let W be the eigenspace corresponding to lambda, E lambda. This is the invariant. So let's see. What happens if I apply T to a vector V in E lambda? What do I get? E lambda was the eigenspace, right? That is the null space of P minus lambda identity. So what is T of V? T of V equals lambda times V. It's an eigenvector, right? The eigenspace of lambda is the set of all eigenvectors. An eigenvector for lambda has this property, T of V equals lambda V. All right, so T of V equals lambda V. So are we still in E lambda? Yeah, because E lambda is a subspace, it contains V. It's closed under scalar multiplication. It contains lambda V as well. Okay. One more. So T is a linear transformation from V to V. X is a non-zero vector in V. Define W to be the following set. The span of the following set of vectors, x, p of x, t squared of x, where by squared we mean t of x, not multiplication, composition. Then t cubed, t composed with t 3 times. I'll do this infinitely many times. So all the powers through composition of t will be in that set. And then you take the span. So I'm taking all the possible linear combinations of such things. Being a span is automatically a subspace, right? The span of any set of vectors is a subspace. Subspace of V. But it is a T invariant subspace. Why is it T invariant? Well, take an arbitrary vector in there. What does it look like? A1 x plus A2 t of x plus A3 t squared, so t of x, plus on, right? Just a linear combination of as many vectors you want in there. But T is a linear transformation, so it behaves nicely with respect to linear combinations. So it's just going to go over right inside there. So this is A1 T of x plus A2 times what? T of x, so T squared, plus A3 T cubed, and so on. So every time I'm increasing the degree by 1, but what I get in the end is still part of my set. W is T invariant, and it has a special name. It is called the T cyclic subspace of V generated by X. And this subspace, not only that is T invariant, but is going to have some very nice properties and is going to play a key role in the Cayley-Hamilton theorem. I'll do that next time. I'll just stop here.